Shall we start?
Is it too hot?
It's okay, I think. Yeah, switch it. It's there anyway.
We can
increase the, yeah. But I think maybe there will be sound coming. Yeah, I think it's okay. Fine, should be fine, I think. Shall we get started?
Yeah.
Or wait for a couple of minutes? I think.
Yeah, maybe in a minute.
In a minute, yeah. We can start, yeah. Okay, so we'll start. We have looked at the idea of rheometers as instruments and the basic variables that are of interest to us in terms of when we want to say we want to understand the deformation behavior of materials. It's basically interrelations between stress, strain and strain rate and them at present instant of time or the current state as a function of whatever has happened in the past. And so one more short lecture on some aspects of what one should look for while doing these measurements before we start looking at all the measurements and different types of class of behavior. So in this particular section, we look at some aspects of the assumptions that go into making cone and plate geometry measurement possible. And since we are making all these assumptions, what are the ways and opportunities by which these assumptions may get violated? So one should watch for those. And while I am discussing cone and plate, in between I'll also slip into some discussion related to parallel plate. And the set of problems that we normally encounter are given here. I mean, so it could be due to, we've been talking about one-dimensional flow, and whenever that gets violated, that's going to lead to issue in terms of what we are measuring, not really related to what we think we want to measure. And we've also mentioned no slip condition already. And so we will look at some of these aspects as we go along. And so in summary, the idea of a rheometric flow in which measurement of rheology is possible is first a decision of what type of flow to impose, so that we have either the diagonal elements of interest predominantly or the non-diagonal elements. And then we generally tend to impose a flow which is one-dimensional, well-defined flow of course, but quite often one-dimensional, or in case of extensional flows, it will always be a three-dimensional flow, but the velocities and deformation will be related to each other. many of the materials that we discuss, whether these are suspensions or polymeric systems, these are incompressible materials. And so therefore, there is a certain, there's a constraints imposed based on mass balance or conservation of mass as to how material can respond to deformation. So basically, volume has to remain constant, and therefore the deformation is related, components are related to each other, especially the diagonal components. And we impose this narrow gap to ensure inertial effects are negligible, so that the Reynolds number for the flows are exceedingly small. And we will see some effect of the inertial effects being dominant in some examples results. And then we generally impose a controlled condition on the material, which could be a controlled strain rate, a constant strain rate. It could be a constant stress or a constant strain, or it could be an oscillatory input, time varying input. And of course, in principle, the material response, if I do, let's say, and characterize the material response in one such forcing, should be related to the material response in another forcing. There are sometimes challenges in terms of extending understanding from one type of response to the other. But the expectation is that hopefully if I characterize one or two of them and explain them well, then I should be able to predict what might happen in the in an additional scenario. And so the cone and plate geometry, the way it's constructed, the angle is very small. So this is sort of 1 to 4 degrees. So it's extremely small cone angle. And the gap is also exceedingly small. So generally the radii could be of the order of 10 to 25 millimeter. And the gaps that you see would be around 50 micrometers. So you can see that it's an extremely thin sample. Given that we are rotating this, we can describe this using a spherical coordinate system with basically radius, then this angle as phi, and then angle from here as theta. So this is the description in which we describe the fluid mechanics of a material which is being sheared. And so if you look at this scenario, then we largely have velocity only in phi direction. There is no motion in r direction and there is no motion in theta direction. So this is, so by imposing a flow in phi direction, this is the one-dimensional flow that we impose on the material. And then V phi is a function of r, because as you go further down in the cone velocity, the tip velocity here is what you are controlling. And if, let's say, this rotation is at some, let's consider right now constant rotation rate omega, then anywhere here velocity is basically omega times r, because that's the velocity with which the rotational speed with which cone is rotating. And it's a function of theta also. So when theta is equal to pi by 2, we have velocity as 0. Right? That's the bottom plate. Theta is being measured from there, so pi by 2 is the bottom plate, their velocity is 0. And theta is equal to this cone angle, velocity is r omega. And the way the construction of this cone allows us to make this particular judgment that the variation of velocity with respect to theta is going to be much larger than the variation with respect to r. Right? Because if you look at the variation is basically variation V phi varies from 0 to omega r, right? That's the variation. Maybe I'll just write it in So delta V phi is omega r minus 0. And if you look at delta r, that's this number. So that's a fairly large number. It's the radius. And on the other hand, delta theta, the r delta theta actually, that distance is fairly small. And so therefore, the variation in theta direction is much more compared to the r direction. And so in the overall governing equation and analyzing the fluid mechanics of this flow, this is a judgment which will have to be incorporated, because velocity by definition is a function of r and theta, and there would be changes as you go along. Material points which are placed at different r, velocity does change in r. Yeah.
So this r, it is the r vector, right?
Yeah, no, so the way I have indicated right now is just the r coordinate.
R,
Coordinate. So r, theta, phi are the three coordinates.
okay, I see. No, because I was wondering that r should be in plane of the bottom plane.
No, it's a spherical this thing, right? So it's not
Okay.
r only in the polar sort of coordinate. R is encompassing the whole space.
Okay.
Yeah.
I see.
So that's why it's a
Yeah, in 3 dimensions.
yeah 3 dimension. Yeah. Any other question? One other feature that we can see is if you look at any, let's say, one particular value of r, right? So let's say I just draw this one particular value of r, all the points which are located. What you can see is velocity at one particular theta is omega r, and another theta it's 0. Right, so there is a distance over which velocity goes from omega r to 0. And if you look at another r value, again value here is omega r, and again value here is 0. But you can see that the omega r itself is different, and the gap over which the velocity goes is also different. So one feature of this cone, the way it's constructed, we will see is the deformation rate, which is effectively omega r by the distance over which the velocity, basically this value, right? So they wanted to take some things, is it? Okay. Thankfully, you will be able to cut out some things right before you put out. Okay. So one advantage of this, we've been saying that, look, as far as deformation behavior of this material goes, strain and strain rate and stress may be related to each other, but you would want to subject the material to a uniform strain rate and strain. So in this geometry, it is possible. This is not going to be the case in parallel plate, where we will see as you go outward in R, the strain rate or deformation will keep on increasing. So therefore, that's another advantage of this geometry from a rheometric perspective, that you are imposing uniform deformation throughout the geometry. So in summary, basically, small angle. There is a truncation at the bottom, so that you don't have, that's largely an experimental effect. Then you have diameters which are order of magnitude large compared to the fixed gap, which is 3 orders of magnitude lower. And compared to other geometries, it's a relatively smaller amount of sample. And so for any general class of fluids, the governing equation, since it's incompressible material, you have the divergence of velocity 0, and then the linear momentum balance, which basically even for an unknown stress, see, many times what we are measuring, we don't really know what is the relationship between stress and strain rate. In fact, that is what is the purpose of doing all these experiments. So in terms of linear momentum balance, this is how the overall governing equation would be. So it would be of our interest to do the measurement irrespective of the model. What I'm going to do in today's lecture is just show that, if it's Newtonian fluid, then how does this measurement happen? But even if we don't know the fluid, at least in cone and plate case, we can still get the stresses and strain rates, as long as we maintain the velocity the way we have said, that it's one dimensional, only V5 velocity, and it's only function of r and theta. So if you look at basically the maybe we'll now what we'll do is go through some of these before looking at the governing equation. What are the features? We basically impose a one-dimensional flow. I have mentioned all of these, that flow is only in phi direction, where velocity is function of r and theta. And again, given the material symmetry argument that we discussed earlier, we will have only these components which are of interest. So tau rr, tau theta theta, tau phi phi, which could arise in the material, even though we are imposing only simple shear flow, and then tau theta phi, because del v phi by del theta is the shear that is being imposed on the material. And the fact that this one-dimensional flow could break down, right? It could be due to several effects, and one is inertia, in the sense that we have a circular motion, and terms like rho v theta square by r or rho v phi squared by r, and these kind of terms can lead to basically a radial flow. Once radial flow starts, because it's contained due to surface tension at the end, it will also start a theta motion. So that's why you can have secondary flows which are caused due to inertia. This is something we discussed, right? That normal stresses could lead to flows, and if that happens, then again it will lead to problems in terms of how our analysis goes. There could be, we are assuming, perfect instrument sort of construction. We are saying that there is no wobbling when it's rotating. The gaps are fairly small. So any 90 degree, this cone is, the shaft is there and the plate is at 90 degrees. So all of these can have, in 60s, 70s, and anyway, today I'll show you one example. That a lot of work has gone on in quantitative rheometry to say that what if, there's a 1 degree sort of wobble, then how much will it influence the measurement that you are making and things like that. And then there could be, additional inertial effects in terms of sort of nonlinear dynamics setting in, turbulence setting in for low viscosity fluids. So basically, one of the things is that judgment that we really need is what would happen, right? How would it affect the measurements? A priori, we don't know that whether any of these is there. Of course, in the last 20 years, one advantage that is now there is we can do flow visualization. So we can use microscopes and other methods to actually image the flow and make sure that it does conform to the one-dimensional situation. But could there be some systematic signatures in the behavior that could lead us to, think about that maybe we have this violated. So that's something one always has to guard against. So generally, of course, when would this idea that secondary flows are important, when would that be possible? When you have extremely high shear rate. Inertia is also important at high frequency, because you have an oscillation, and so you are assuming that the geometry went to the extreme position and then reversed, but the fluid may just continue to still sort of travel and then due to inertia and then come back later on. So again, low viscosity fluids in oscillatory shear one has to be very careful about. In fact, there are various times we will define this storage modulus as a function of frequency. You might have some behavior and then suddenly there will be a catastrophic sort of decrease in terms of the measurement. And of course, many times we would like to interpret this as a material microstructure phenomenon. And so, but we can do analysis and show that this is actually due to those inertial effects. And so that's something I have not included in today's lecture, but if there is interest, maybe tomorrow I can discuss that. And then there could be interfacial instabilities that I'll discuss again. And significant normal stresses are also, whenever there are significant normal stresses, one always has to worry about whether secondary flows are being affected. So coming back to the governing equations themselves, so what I have done here is written the mass balance, of course, is trivial. It's identically satisfied, but we have this rho V phi squared R term on the left hand side, and that's why low Reynolds number and gaps being very small is needed, so that we could ignore the left hand side term, and so that inertial effect are neglected. There is tau theta theta, tau phi phi, tau RR is there, and so all these terms can contribute. This is equation of motion, and the other one is also V phi squared cot theta by R. So there are, you can see that many terms are significant, and then the tau theta phi term also. So tau theta phi, and what you can see is we can do some simplifications given that theta is a very small number. So sin theta we can approximate, right, close to 1 basically. There is not much change. This is sin pi by 2 it will end up being, because theta 0 is the vertical axis and pi by 2 is the bottom axis. So the theta is very close to pi by 2 all the time. So analysis, actually all of these are going into our final sort of estimation of the properties. So therefore angle, effect of angle is there. So that's why generally we will have cones of 1 or 2 different angles, and we can, if there is doubt in terms of quantitative nature of our measurements, we do measurements with both and then try to see how much of an error there could be. And for a Newtonian fluid, so I have written those terms now. So mass balance again is trivial. What you can see is this is now all written in terms of velocities, because for Newtonian fluids, the stress tensor is basically related to the strain rate tensor proportionally, right? Newton's law of viscosity, stress is proportional to shear rate. And so, and D is written in terms of velocities, so the Navier-Stokes equations are basically simplified. And so, if we keep inertial terms negligible, then we don't really have to worry about the R and theta equations. We only have to worry about the V phi equation. And in V phi equation, we have variation of phi with respect to R and then variation of phi with respect to theta. And so, to again proceed further, what we say is this term is order of magnitude smaller than this term, right? So we basically say that we can ignore one of the terms, and then going forward, okay. Okay, so going forward, what eventually you will see the sin theta can be sort of almost 1. So this overall equation basically ends up being del square V phi by del theta is 0. And that's the governing equation. And we talked about sort of a very simple situation of a parallel plate flow, which can be easily understood. And in this case also, if you look at the governing equation, it will be del Vx by del y squared equal to 0. So we basically have a very analogous situation where flow is between 2 parallel plates, and only thing is the cone, maybe I'll just draw it. So it's as if the cone has been sort of split into variety of parallel plates. Each concentric ring of material is sort of having a simple shear flow of the parallel plate between 2 parallel plates. So what I mean is one particular concentric ring is moving at omega r, below velocity is 0. You go further down, again it's so it's basically parallel plate flow effectively, and since the gap is also changing, and the velocity is increasing, effectively we have constant strain rate throughout the geometry. And just to sort of talk about what might be an effect, and especially secondary flow, these are some measurements from Shiv Shankar, who's an MS student with me. So this is a silicon fluid, Newtonian fluid. And here, because the gap can be changed in parallel plate, the data is being shown with respect to parallel plate, saying that if you reduce the gap, what happens is you reduce the Reynolds number and reduce the importance of inertial effects. And so 507, which is the black data, you can see that even though it's a Newtonian fluid, at around itself 200 itself, you can see that the velocity is no longer constant. This is a Newtonian fluid, so it should not really have any changes in viscosity. And so this decrease in viscosity, for an unknown material, you could say that, oh, it's a shear thinning material, right? Or is it due to this? So in parallel plate, what you could do is therefore change gap and then see. If it's a material response, then at two different gaps also you should see identical response. But once you look at this data, you know that as you go to smaller and smaller gap, the viscosity is constant for larger and larger shear rate. And in fact, you can see that you can change the shear rate by almost 1.5 orders of magnitude, over which you can still maintain the predominance of one-dimensional flow, and the secondary flows are not very important. So this is something that can be done only in a parallel plate. In a cone and plate, it's not possible. Other thing is, of course, the gaps in cone and plate are naturally smaller, right? In parallel plate, one had to go to 67 microns to see that data is reasonable up to 1000 and thereabouts. In cone and plate, that would be also the case. Yeah.
So this fall is due to secondary flows.
Yeah.
So you can probably show that onset is like inversely proportional to the gap because it is V square by R.
Yeah, exactly. Yeah. So you can do some of these analysis and then actually look at, so that's the way. One is of course to do flow visualization and see whether, you know, at the edges, see, and also it's clear that the velocities are larger towards the edges because omega r. So you would tend to look at secondary flows near the edges. So if you do flow visualization there and if you don't see secondary flows there, you can safely assume that they are not there in the interior most often. And so, but if not, you will have to do some analysis of this kind and then look at scaling and then say that, okay, it corresponds to our understanding. And yeah, just take the mic.
In this plot, how do you know which gap is idealistic for this? Because for this measurement, because there are order of magnitude variation in gap, and suppose you don't know this is a Newtonian fluid, and how do you know you can change the gap, but changing slightly or the measurement won't affect? Because here we have changed order of magnitude gap.
Yeah.
So in this case, if I ask what is the ideal gap for measurement of the viscosity, then what might be the answer?
No, so the question is the other way. So viscosity measurements, I think all of them are doing reasonably. But if let's say I am interested in knowing that does this fluid, see this is basically some silicon oil which is implies that it's a short chain molecule, and it is possible that at very high shear rates it may show non-Newtonian behavior. So given the practical application in which this oil is used, it is used at very high shear rates. So then I am interested in knowing, so at that shear rate, is the sort of measurement reliable or not? That is the question, right? Because here up to 100, all the measurements match. So there, irrespective of the gap, you will get the same result.
Then on what, because the question is like whether your gap is perfect or not, you can change the gap and
no,
see.
It doesn't matter, right? All gaps are perfect.
So then there is with different materials without with change in gap also you can get the response only. Okay.
Right. No, so I don't understand your question. So see, if you maybe you repeat it once more.
My point is, suppose you don't know the property of the sample,
Right.
and you measure one with particular gap,
Right.
and you want to know whether this gap has some artifact in this measurement or not.
Right,
Now, at what gap you will, how much you can change?
Right, right, yeah, yeah. No, so see, there are, what you would do is, you would change the gaps, right? And you look at some of the systematic behavior also. For example, the departure from, first of all, you need some hypothesis whether you expect the fluid to be Newtonian or not. Secondly, you expect the departure to be there. Is the departure, for example, leading to an increase and decrease in viscosity? So you need some hypothesis, and you need some systematic variation. See, for example, in this case, if I go from 500 to 450, there shouldn't be qualitative difference, right? There can be quantitative difference, but so if there is quantitative difference, then it's due to the secondary flow effects and all that. So initially you do your analysis with an order of magnitude gap just to see whether qualitatively you are getting the same feature. Then you do it in a much narrower window to ensure that it's quantitatively also similar. Then you say that it is at least in 400 to 600 range, I am getting quantitatively the same response. If I go to too small a gap, maybe there are material artifacts. If I go to too large a gap, maybe there are inertial effects. So that kind of an analysis you may have to do. So generally for an unknown material, what you do is you do 4 or 5 gaps, and then you choose the range where it seems like inertial effects are not there and structural heterogeneity, the length scales in the material are still much smaller compared to the gap. So in parallel plates, for example, people have chosen from 1.2 mm all the way till 0.3 mm, depending on the material. And so, as we discussed in the morning, that if you are trying to avoid, inertial flows and secondary flows, one would want to go to thinner gap. But if your material, so this is showing sort of a particulate system, and the particle size is 18, 20, 30 microns, that you can see that when you are doing it at larger gaps, you are exploring, material at a bulk scale. But when you start looking at gaps which are narrower, then you are completely measuring systems with the monolayer or bilayer of particles. And then now the effects that arise due to this confinement will dominate. And so clearly you will have to be more careful while analyzing thin gap rheology whenever you have such situation. So this thin gap that I mentioned here for a silicon fluid is okay. But any material which has these kind of things, one needs to be more careful. The other sort of feature is related to the instrument response time itself. We are talking about applying a constant strain rate or changing stress from one value to the other, and most often the instrument itself will require certain amount of time, and quite often the initial time measurements that we do using rheometer are contaminated with the input itself not having reached whatever it is sort of looked at. And so this is something one needs to look at. No slip boundary condition, which is for both bottom and top, is fairly important. We've already discussed this. And again, the question is, what might be the condition for possible violation? And how will the measurements be affected? And so I have one example where these are for 3 different systems. These are the systems which again are known whenever you have foams or emulsions with larger volume fractions, then it's possible that you will have slip at the surface. And what is being proposed is basically you plot, you again do this again in parallel plate. So again in cone that you have slip, again to examine that may be difficult without flow visualization directly. But in parallel plate, again by changing gap, you can, what you can do is, since there is a slip velocity, basically the real shear rate and the apparent shear rate are related to each other through a constant slip which is there. And so the shear rate correction is basically this slip velocity by the gap. And so given this hypothesis, then you can try to plot your data of 1 over h. So like he mentioned again, you do the analysis with respect to how you are changing the gap and what's the shear rate that you observe, and then plot this and then try to back calculate the apparent shear, the true shear rate as well as the slip velocity. And so using this kind of a process, they've been able to quantify the slip velocity in these 3 systems, saying that it's much more in the case of foam, and it's much less significant in case of other emulsions. And then the again analysis of power law dependence of the slip velocity on the difference compared to a yield stress of that particular material. Those kind of analysis will again help with making sure that we understand that yes, it is indeed slip, and that slip is related to how the material force chains form, and then they move as a plastic flow, and therefore slip is there in the system. So that kind of an analysis will then hopefully lead to a better comprehension of what the data says. One other feature which is related to thin gap, since we are discussing in both the cases varying the gap, is the fact that how does instrument decide to set the gap. So basically you have the bottom and top plate, and the instrument first has to figure out where the bottom plate is. So generally we will give the instruction to the instrument that go to the 0 gap. So what instrument will do is lower the gap, and whenever, because of the air gap between the two, eventually air is being squeezed out, and because of that the pressure increases and there is a normal force. So instrument senses that, and then it through its algorithm declares that I have reached the bottom plate. You would not really do a contact. It's based on this increase. And so 0 gap error is always present in these instruments. It's never perfectly 0. It's based on these normal stress increase due to an air gap which is being squeezed out between this as the geometry is coming down, and some algorithm of how is the nature of this increase, and therefore how far away is the bottom plate. So this estimate can, it's an estimate in the end that instrument does, and so there can be an error of about 10 to 15 microns in the way the 0 gap is being set. The instrument thinks the 0 gap it has some level, but it can be easily 10-15 microns different from that. And so this data right now on the left hand side is the measured viscosity as a function of gap, and there is a cone and plate data also there, which is the purple one. And what you can see is at the low rate there is an issue related to instrument sensitivity. At the high rate there is an issue related to inertia, as we discussed. But even in the place where the viscosity is supposed to be constant, and it's this measurement of course was done on a suspension, so we are struggling with this idea that is this a real effect, and how far are we going. But then what you can do is, again you can say that I have copied and pasted, but I forgot to change this equation. So a similar equation which talks about given that so what you have is basically what the instrument is thinking is that it is applying this shear rate, but in actually what it has applied is this shear rate, right? So the two shear rates are different. So therefore we need to correct for that, given that there is a gap error of what instrument thinks is 0 and what. Again you can do a systematic analysis, and this straight line actually shows that plot, that if the data lie on one straight line, then we can back calculate the exact gap error, and then if we correct for that, then you can see that data collapses on top of each other. So therefore gap correction is significant, and it's significant for gaps such as 100, 600, because it's now 10% or 20% of the overall gap. When the gaps are large, then the gap correction is not so important. And so this is also something which becomes important if we start exploring material under confinement. So now coming back to cone and plate, where we don't really change the gap, and so for a Newtonian fluid, incompressible fluid, as I said, we ignore sine theta and we ignore this term, and so we largely are only looking at variation of v phi, and so that simplifies and gives us the overall velocity profile, which is like a linear velocity profile. The other thing which we have sort of ignored is when we have the cone and we put the fluid in it, what's the nature of this interface? So it's being assumed that it's spherical. It's a spherical cap. The overall analysis is being done within that, so that the radius of curvature basically is defined based on this, is the assumption. Now whether it remains so or whether it deforms, that can lead to again, that will again lead to secondary flows, edge fracture and so on. And that can change the measure. So there are instabilities and edge fracture which are associated with these, and again similar questions. And now this is one example of work now at 10-15-year-old, where they are proposing a different cone and plate geometry to make sure that the edge fracture effect do not affect the overall measurement. Right? How do they do this? Is they call it a cone partition plate geometry. So if you look at it, this is the cone that we've been talking about, right? So this is the cone, and the plate is only here, and so the edge of the sample is much further down. And so you are making sure, but then you make measurements along different radii. So you make measurements here also, you make measurements here also. So you can vary this amount to which you can fill the sample, and then therefore you can make the measurements and then try to back calculate. So in this kind of a geometry, hopefully with time, whatever edge effect are there, those you should be able to back calculate and remove. There is also one little more recent work which asks this question, that sometimes I'm worried about whether when I fill the sample and it's a little less filled, let me overfill it. And so overfill is something like this, that it's for parallel plate again, that you have basically material which is more than what it is. And so does this have an influence? And so they did systematic experiments of degree of overfill, and then looked at how much may be the error in the viscosity that is being measured across different types of geometries, and they are getting some significant systematic errors. They are also able to explain this using some fluid mechanical simulations, some CFD simulations, to try to justify that why is this change. So many of these effects are important when we are trying to make quantitative judgments. For qualitative phenomena, maybe some of them may not be as important. And so, of course, shear banding is an important factor which I have not discussed here. But the fact that the material itself may break into regions of high shear and low shear, and therefore the commanded shear rate is something in between the high and the low shear rate. There are various materials that do that, and again it's not clear, the signatures of shear banding and some other nonlinear viscoelastic features look similar at the analysis level. So unless we do flow visualization or some other systematic analysis, it may be difficult to immediately pinpoint some of these effects. And there can be transients in flow, which is the material response itself. And when I talked about thixotropy tomorrow, we will see that the material structure evolution itself is reasonably slow, or aging materials, that is the response, what is the effect due to the aging structure of the material, and is the drift is not an instrument drift but a sample drift. So that again is something we have to worry about. And last is basically the question of, many of these are heavily viscous materials and the dissipation can cause an effect. But again, gap here is an important feature. So if you lower the gap, given the conductivity of the material, then energy can be sort of dissipated away, and so temperature increase can be kept under control, and so you can assume isothermal response. So with that, I think I've summed up sort of some of the features related to quantitative rheometry that one has to watch out for. Any questions?
In slide number 15, I think you showed some velocity, slipping velocity. There is a power law after that also.
Right, yeah.
Yeah, and what I missed that part. What does that power law indicates?
No. So see, the power law is with respect to this difference from the yield stress. So the further away you go from the yield stress, the more is the slip.
No, different sample you have different power law.
Yeah. That's
so
right. Yeah.
Are they indicating something depending upon how much slope is it?
That would be the analysis, right? Yeah. So you would look at the natures of what these emulsions are and the bubbles and how are they responding and why do they, one is one power law with one say scaling, the other one is power law with another scaling, would be the analysis that would be part of this paper. Yeah. I don't know actually, I haven't gone through, and I don't remember right now whether the number here and number here, how do they rationalize it? But yeah, that's the purpose of the paper.
Another point where you fracture plane at the fracture, if it is not spherical, let's say, and can you give some examples where actually there is, because in large granular system, let's say your granular particle size is very large, let's say, there you expect deformation at the boundary.
Even polymer melt would do this. A polymer melt would do these, and again partly because of normal stress differences that are there in the system and so on. So
only fluids, pure fluid only you can expect the spherical things, I think.
Okay. You are saying where would, so you are saying why would you assume spherical shape? Huh?
Yeah, because it's a realistic system, it should not be like this, I think.
Yeah, no, so see, even in suspensions, generally you are looking at 40-50% by volume, right? So other 50% is the dominant, and you would assume that the particles are not adsorbed on the interface, right, of these suspensions. And then in that case, it may be okay. But if let's say they go to the interface preferentially, then anyway you have a very different system. So yeah, if they remain in the bulk, then I think it's okay. I mean,
let's say yield stress system you take.
Yeah, I mean, as long as you are still, the balance of is still there. So, okay. and it's, see, it's still a homogeneous system, right? See, but there are other features associated with particulate system that you could have migration of particles, you can have particle rich and particle lean regions because of hydrodynamics, right? So those are features which are also there. But the interface being not spherical, I'm not so this thing that just because particles are there, it will lead to, because particles are so small in compared to this scale, right?
Okay.
In cone and plate, you should look at only those systems which are 5 microns and smaller, right? You should not look at, and so therefore then they are small compared to the perturbations that they cause to the interface is still going to be small. But you are right that if larger particles are there, then one always has to worry about how much does the edge influence. In fact, so the propellant system that I showed in the morning, the inertial effects start playing a role at 1 per second and 0.5 per second and all that. So only at exceedingly low shear rates one can make a viscometric one-dimensional flow in that kind of a material system.
Because of very large particles.
Very large particles and
some 300 microns.
Yeah. And also very high solids loading, right? Effectively, it's by volume it's 55-60% particles.
Okay.
Though by weight it is 80%, by volume also it's still very significant. Maybe we can take a 2-minute break to stretch because this is post lunch and then resume. In the sense, last time I just kept quiet, but maybe you can also stretch given that it's post lunch. And then we'll start.
Parallel plane,
Mhm.
when you decrease the gap,
Hmm.
so also you always run into problem with the smaller reliable shear rate that you are applying.
Hmm. In the sense?
In the sense the stress, the instrument has a torque resolution limit.
Ha. No, but
so when you reduce the gap,
right.
so then
No, but the torque may increase, right? Because you are lowering the gap and increasing it's possible to go to higher strain rates. So you can again overcome the limitation by going to higher strain rates and then going to torque which are higher than the sensitivity. So lowering the gap allows you that benefit.
what about the values that are on the left side?
That will be a problem, yeah.
Because for that you need to have the higher gap so that
More material.
so that you will be able to rely on smaller shear rates.
Yeah.
So that can be
Yeah. So in the data actually you saw that the lower gaps, the lower thing was falling little more quicker. Yeah, that's
that
true.
can have a systematic
Yeah, influence. Yeah. Shall I start? Already a bit late, I think, 5-10 minutes, because I should have wound that up in 45 minutes. It is okay. Anyway, this lecture will wind up not today but tomorrow. So don't get scared by that 47 slides. So I'll plan only half of it today, and then remaining we'll see tomorrow. Okay. Yeah, so we'll look at now sort of a series of characteristics that we can get using rheometers, and then look at class of behavior. So the first one we'll look at is linear response, which implies smaller perturbation either in stress or strain, and in that we will look at this idea of mechanical relaxation process, and the Maxwell model as a simple model which describes the relaxation in a material. And we look at oscillatory shear as way of characterizing the response. This is very analogous to dielectric spectroscopy, or basically frequency dependent response, frequency dependent susceptibility in other domains also. So we have frequency dependent modulus or frequency dependent viscosity, depending on what we choose to look at. And then have a small modification to Maxwell model, which sort of is more appropriate for hydrogels and gels and cross-link systems or sample spanning network systems, so that we can look at their response also, and briefly touch upon the fact that there are spectrum of relaxation time when we do this mechanical spectroscopy, and we also have an equivalence between time and temperature, and this idea has practical relevance in engineering applications in terms of what we call accelerated testing. So for a product that I am designing for 25 years, I can test it at higher temperatures and then confirm that it is not going to degrade in 25 years. So this is only possible if there is an equivalence between time and temperature, and that's what we exploit also to gain quantitative material response and characterize its rheology over very wide time scales, even though what's accessible to us in experiments is only a short time scale. So we basically do the testing in different temperatures and then change it to various time scales. And then some sort of discussion related to our work and some work from the literature, where you are going from this liquid to more solid-like behavior. And so the process of gelation and rheology, especially oscillatory rheology during this transition. So this is how, I generally order my lecture and motivate it, saying that material by itself is not one type of the other. We will have to sort of look at the context and what we are after, decide what class of response that I am interested in. So a polymer melt, I could choose to decide to look at it as a viscous material if I am only interested in transporting it over a 1 kilometer pipeline, because it's largely going to be a steady flow, and even though its viscosity is not constant, I can still choose to ignore viscoelastic effects. I can say it's a viscous, nonlinear viscous fluid, but nonetheless a viscous fluid, so that there is no change in geometry, no change with time. So when I am interested in kilometers of pipeline transport, crude oil, which is actually a viscoelastic fluid, but we consider it largely a Newtonian or at most a nonlinear viscous fluid. So therefore, generally we would need to choose a class of response, and then based on that we say, okay, what might be material function that might be useful to look at this class of response. So if we say, let's say viscoelastic, then we say we can then look at variety of material functions which can be used to quantify the response using rheology. And this is done by doing one variable or the other constant. And so in literature over historical sort of progression, we have had many of these properties which are defined. If you look at sort of Hooke's law of elasticity, we define the material using a modulus. But we also have the flexibility of defining a constant based on strain over stress, which is called a compliance. It just so happens that we don't use compliance as often, we just use modulus. So similarly in this rheology also, there have been several definitions of different variables, and since we also have control over stress or strain rate, so we can keep either of them constant and then measure the others, and therefore define all these different material functions. And then in parallel, just look at some model which sort of gives us some grounding in terms of what's the response compared to the real material that we are trying to organize. And so viscous and elastic response, sort of the current state of stress is related to the current state of strain rate in a viscous material. Whether it's a power law fluid or many of the other sort of first non-Newtonian fluid, when we only learn about this shear thinning or pseudoplastic and power law thinning fluids, where we are only worried about viscosity as a material function. So in that case, our hypothesis is that there are no elastic effects and viscosity is completely determining the material. So therefore, that material also, the material state is completely specified based on current states. On the other hand, the Hookean solid kind of a response is current state of stress depend on current state of strain. In this case, strain rate has no influence. It doesn't matter how fast or slow I get to a particular value of deformation. The only thing is the deformation itself. And looking at a perfectly crystalline solid, one is only saying that, look, the unit cell has got deformed, and the relative displacement between atoms, the way it has changed, only that determines the energy, and that's what has got translated to the stress. So therefore, stress and strain are related to each other purely based on this idea of configuration dependent only on energy, and that is basically internal energy of the system. On the other hand, in case of a fluid, we have the liquids and gases, molecules going around. So it's a perfectly dissipative system, because as soon as you apply a constant stress, a steady state is set in the system. System reaches a steady state, in which case it keeps on flowing with a velocity and a constant velocity gradient and a constant strain rate, and the stress multiplied by the strain rate is the dissipation rate in the material. So as long as there is a mechanical energy input into the system, there is a constant dissipation that's happening in the system. In this case, the energy is being stored, and so as soon as you release the energy, in case of solid, the crystalline unit cell again comes back to the minimum energy configuration, and basically you can say that the mechanical energy which was stored has been recovered. While in case of fluids, there is no such thing, there is no returning back, because the energy has been dissipated. So therefore, viscous response is the dissipative response, while the elastic response is storage. And what we are doing in viscoelasticity is looking at both combinations, and there are relative contributions, right? And these relative contributions would depend on the time scale of our examination. And the way we formulate viscoelasticity can therefore be two different ways. We can say that the current states of stress, strain rate, and all the other rates are related to each other, because this is a more complex response of the material, and variable, which is, let's say, stress and strain, are related to each other through not just themselves but their rates, and they are higher order rates. Or we could also say that current state of stress, depends on whatever is all the summed past history of the deformation. So sort of this is a differential, in mathematical terms, this will lead to a differential equation of constitutive relation, and the other one will lead to an integral statement. And both of these models are around. If you look at historically how phenomenological models have been used to describe rheological response of materials. And the other expectation that we always test against is there will be some terminal response, given that time scale of our examination gives a certain kind of response. If we do a very large time scale experiment, or if we do a very short time scale experiment, I would see one of the terminal response. So I might see a viscous response at very large times. I might see a very elastic response at very short time scale. So I need to examine the material at these extremes and make sure that it conforms to my expectation of the terminal response. And so the mechanical relaxation as an idea is basically based on application of a constant strain. And so for an idealized solid, which is basically an elastic material, if I apply a constant strain, I have to apply a constant stress, right, to keep the deformation constant. Since I apply a constant strain, I will have to apply a force which will relate to a constant stress. And so, as I mentioned, the crystalline lattice remains in the deformed arrangement as long as the strain is applied. So if I apply the strain, which means I will have to impose a force, as long as I keep the strain fixed, the same amount of force will need to be imposed on the material. And so there is no relaxation process in the system. The stored energy remains and there is no decrease in it, and there is no decrease in the stress which is required to keep the material at the new deformation. So at atomic scale, basically you are deforming and changing the unit cell, and it remains so. Of course, if there are relaxation processes such as crystalline defects and diffusional processes which could lead to some readjustments, then eventually that is a dissipative process that might happen in crystalline solids also, right? So, but those time scales are usually much smaller compared to, let's say, this mechanical response, or their contributions could be much less in terms of determining the stress. So therefore, this idealized solid, then we can say has no relaxation. It's not relaxing at all. On the other hand, for a fluid which is idealized, if a strain is applied, a stress has to be applied to deform. So I take fluid between two plates, I move the plate. During this, I will have to apply force. But to keep the plate in the new position, I don't have to apply any force. That's the same thing that I mentioned, that a jar of fluid and a thin film both don't require any force. But during pouring, I will need to do some force application. So therefore, once the strain is reached, no further stress is required. So basically, the randomly colliding molecules have completely dissipated whatever force was applied, whatever mechanical energy was input into the system to take it to a new configuration. And so basically, there was an instantaneous relaxation or perfect dissipation in the material. So from a mechanical point of view, we have an example of a material which is relaxing instantaneously and one which never relaxes. And so viscoelastic material will have a relaxation time which is finite, and more importantly, it might have a spectrum of relaxation time depending on the physical mechanisms. So therefore, time scale of relaxation process for solid is infinite, and for a viscous response is 0. And for most real viscoelastic materials, we would have something in between. And so each of the relaxation process that is leading to this interplay of stress strain relation is associated with a relaxation time. We refer to each and every relaxation time corresponding to a mode. So there are several relaxation modes in the material, and basically depending on the time scale of interest, a particular relaxation mode may be frozen, like the relaxation mode of defect diffusion in case of a crystalline solid is effectively frozen for many mechanical interest, or occurs instantaneously like the gaseous or liquid molecule motion, or it could have something in between. And so therefore we can have a spectrum of relaxation processes which are important for at a particular instant of time. This is a hypothetical sort of number which is not used as much as but it's always introduced during rheological introduction, is the Deborah number, which basically compares the relaxation time of the material, which is 0 for viscous and infinite for elastic, and the experimented or the examination time scale. And it's the ratio between these two which determines whether the material is more viscous or more elastic based on Deborah. So if Deborah is very small, then relaxation time is very low, or experimentation time is very large, and effectively leading to dissipation of energy. And so the common example that I give is basically plate tectonics for geologists. When they are looking at the motion of Earth's top crust, the primitive model they will choose is Newtonian fluid. But for us, Earth is reasonably solid. But again, for somebody who is looking at the effect of this Earth with combination with water, you have sudden transitions from a solid to liquid of this mud slides and so on, right? So therefore it depends on what's the constitution of this earth, what's the time scale over which one is interested in, then the behavior can again be different. And so the Maxwell model, which basically combines phenomenologically a viscous response and a elastic response, because this two terms are viscous response itself. And if you look at these two terms, it's lambda del tau yx by del t equal to eta del gamma yx by del t. And one thing that we should remember, that I wrote this term where strain, gamma is strain and this is strain rate, and I can do this because we are talking about small deformations. So infinitesimal strain, the way we defined earlier, is useful here because all of this is for linear response for small perturbations. Otherwise, this measure of strain is not sufficient to describe the deformation in the material. Moreover, a partial derivative is not the rate of change of strain. One would have to look at strain tensor, its convected rate will give us the strain rate. It so happens that the strain that I defined in the morning and its convected rate is the strain rate tensor that I defined, okay, in terms of velocity gradient. But this is what one would have to do in general. So this relaxation time gives a clear indication of what's the dominant response of the material. When lambda is close to 0, you get Newtonian response, and when lambda is infinity, you get the elastic response. And the first sort of type of experiment that one can do, we've been discussing it, that you apply a constant strain. And so when you apply a constant strain, the Maxwell model gives you an exponential decay in stress. So you have the stress as a function of time. For a solid, it will remain constant, and for a fluid, it will decay instantaneously. But for a viscoelastic Maxwell fluid, it's a decay, and the decay is defined by the relaxation time lambda. And this is the integral formulation of the same equation. We can cast the first order ODE in terms of an integral, and this kernel is basically the relaxation that you saw here, right? So we define something called a relaxation modulus. Which is the stress divided by the strain, the constant strain which was applied on the material, and so it's an exponentially decaying function. So from a Hookean point of view, again, because the modulus is always defined and it's a constant, for a viscoelastic Maxwell fluid, the modulus is a function of time, and it decays to 0 over long times. The other thing that you should, you can sort of appreciate is, if you are doing an experiment and you do experiment at different strains, and the modulus, relaxation modulus is a function of that strain, then you are in the nonlinear regime. So in the linear regime, the modulus is not dependent on the strain which is being applied on the system. It's only a function of time. So that's why this is called a material function. It's a function which characterizes the material. For different materials with different relaxation times, the decay would be different. Secondly, the functional form itself could be different also. For Maxwell model, the functional form is exponential. But some other models, you could have different functional forms for the relaxation modulus. So this relaxation modulus is the kernel in this expression, and if you look at this term, is like a strain. This is like a delta gamma. So it's the strain which is applied between T and T plus delta T, and this is the modulus with which you are applying. So this is stress into strain. But the modulus that you are multiplying keeps on changing as T minus T prime. When you are present time, then this modulus is very high. When you go back much more in time, this modulus actually falls off to 0. So this is like saying that the material has a fading memory. The immediate past strain is getting weight with respect to higher modulus. Something which is much further in time, deformation will get weighed with respect to much lower weightage. And so the current state of stress is determined based on all the past history, but the immediate past gets much more influence. And so I'll just repeat that relaxation modulus, we define it as a material function. It's basically the stress which is being measured as a function of time divided by the strain which was applied, which is a constant strain. And since it's a linear response, relaxation modulus is only a function of time. So we could have superposition that if you apply multiple strain inputs, you can measure the multiple stress outputs, and then if I apply the strain summed up together, I will get a response which is basically summation of all the stress responses. So superposition is also possible in this. Any questions so far? So now we will look at yeah.
No, so that superposition, it comes from linear response,
Yes.
right? For
Yeah.
any model, I think as long as
Yeah.
it is linear response,
yeah.
the superposition
is fine, yeah. So now we will look at oscillatory shear, and a lot of experimental measurements that I'll talk about will be with respect to this oscillatory shear. And so we apply a constant, we apply a strain with a constant amplitude, and then measure the stress. And given that this is a linear response, the stress is at the same frequency as the input strain. Because of the viscous or elastic nature, there is a phase lag between the stress and strain. Because for a Hookean solid, what we will see is the stress will be basically G times gamma theta phi sine omega t. So this and this are in phase. And for Newtonian fluid, they will be out of phase because this is a derivative of strain. Newtonian fluid, stress is proportional to strain rate. So there is a pi by 2 phase lag between stress and strain signal. So for a general viscoelastic fluid, delta will be from 0 to pi by 2. 0 signifying elastic, pi by 2 signifying viscous. And therefore I can write this time as in phase with strain and out of phase with strain. And the coefficients are defined as the storage modulus signifying solid-like response, and out of phase, which is signifying as viscous or loss or dissipation, right? So loss meaning dissipation. So very analogous to permittivity and dielectric laws, these two signals. And so for Maxwell model in oscillatory shear, we have the coefficients given by this, where the G prime is omega squared lambda squared and 1 plus omega squared lambda squared. One feature we can see is if omega is very small, right, which means very low frequency response, which implies that I am giving material sufficient time, right, the frequency is very low. So in that case, we can ignore this omega lambda square with respect to 1. And so therefore G prime is proportional to omega squared at very low frequency. And on the other hand, G double prime is proportional to omega. So this is a standard viscous response, terminal response that we would check for. And polymer melts or polymer solutions or various colloidal suspensions would show this kind of a terminal response. if there is a lack of terminal response, then immediately we would say that there are some sample spanning networks, and the network points are, even if temporary, the time scale associated with their remaining in bond is much higher. So they are like sticky points, and the time scales over which the stickiness remains is much higher. So that we now start getting responses which are not corresponding to omega squared and omega, but much more less dependency. On the other hand, if you have omega very large, then G prime becomes constant. So that's the elastic response, the glassy, so-called glassy state. So in Maxwell model, basically you go from a perfectly viscous to completely glassy material, and this happens in Maxwell model within 2 decades. Sorry. Yeah. So as you go from sort of 2 decades, right, this transition happens in case of a Maxwell model. Real materials don't show this change in just 2 decades. In the sense, if you look here, the omega lambda appears as a group. So omega lambda equal to 0.1, you will basically get 1.01 in the denominator, close to 1. But omega lambda equal to 10 gives you 100. So 100 is dominant, 1 can be ignored. So within a span of 2 orders of magnitude, you go from one response to the other. While most other materials might have 4, 5, 6, 8 orders of magnitude in response before you go from perfectly viscous to a perfectly elastic response. And so that again clearly indicates that there is a several relaxation processes which, even if some are not active in some frequency, they will become active at some other frequency. So depending on the time scale of interest, you may have the relaxation process perfectly dissipating, or it may be perfectly storing, but when you change the frequency, again the contribution changes. And so this is the standard sort of G prime slope 2 and then becoming constant, and this is slope 1 and -1, which the Maxwell model responds. And actually water emulsion at oil and water emulsion at very high drops is one of the few materials which shows Maxwellian response, because otherwise there are not many real materials which show reasonably close behavior to Maxwell response. And so if you look at sort of very, very low frequency, it looks like that the droplets are able to move because the motion is so slow that other droplets are also of course moving, and an individual droplet can move, effectively basically a bulk homogenized motion of the suspension as a homogenized fluid. On the other hand, when you go to very high frequencies, basically each droplet is now in a cage, frozen. There is not enough time for the drop to move, and it is as if it's in a cage, and therefore a glassy kind of a response. Yeah. Yeah. Yeah.
Yeah, so another material that follows the Maxwell model very well is a solution of giant worm-like micelles,
Right,
because
yeah.
that also has a single relaxation time,
Yes, yeah.
wherein the reptation time, which is the diffusion time, is much higher than the breaking time.
Right, yeah. In worm-like micelles, you also have a right, yeah. Then it's, yeah. And so for polymers, this was done more often, where one looks at, rather than looking at the modulus itself, you look at the viscosity, and quite often the complex notation is also used just the way it's used in dielectric response. So you have this viscous viscosity and then the elastic viscosity, right? So just the way we had storage modulus and loss modulus, and then the complex viscosity. So the Maxwell model again shows a complex viscosity, the eta prime varying as decreasing with frequency. So that's sometimes so this is sometimes used mostly in polymer literature, not really other places. Now we will look at just adding a terminal response which is absent in terms of the terminal viscous response. Because if you have these polymer molecules, polymer melt, and if you do sufficiently slow shearing, then what happens is the reptation is possible, entanglement points can slip, and therefore you have basically predominantly viscous response. But if you have cross-linked polymers, then you are preventing basically the slippage of chains past each other, and therefore even if you go to a low frequency, the chains can at most stretch, but they will not be able to slip past each other. So therefore, when you have a deformation, you again have stretching of polymer segments, but there is no slippage, and therefore even at low frequency this material will again have an elastic response. And so rubber is a very common example of this. So at room temperature, rubber is solid and elastic in the sense its storage is higher than its dissipation. G prime is larger than its loss modulus. If you go to very low temperature where you have basically taken it below its glass transition, again G prime is larger than G double prime. So, but you have both of these cases where energy storage dominates, and that's why then we can use rubber band basically where it's perfectly elastic material. So dissipation is absent in case of a rubber band kind of an application. On the other hand, when we are using rubber as a O-ring in an instrument where it's vibrating, right, or vibration isolation, then we are taking recourse to its dissipative capacity to dissipate the vibrations, mechanical energy that's associated with vibrations, and so that it dissipates the energy and does not lead to transmission of energy from one solid body to another solid body. So response basically therefore is high G prime at lower frequencies and high G prime, which is the glassy. So this is the rubbery phase and this is the glassy phase. And this is basically response at fixed temperature, but as I said, I can do the same thing by changing temperature also. And so this is how, if temperature is increased, you come to a rubbery phase, which is most materials like tire and all those things at room temperature are rubbery. But if we take them to, let's say, minus 80 degrees, then they would be glassy and it would shatter, right? Just like any brittle glass would. And this is basically response at a fixed frequency. And so this is a cross-linked gel in which some solvent is there, just to highlight that this change between storage and constant storage modulus at one condition to another. So this is a dry material, so it has a higher storage, but when you go to higher temperature, it becomes rubber, right? So you have this glass transition that's happening in this dry material, but when you start adding more and more solvent to it by exposing it to some solvent condition, its modulus drops in the glassy state, and also the temperature at which it becomes rubbery also keeps on decreasing. So there is a plasticization effect because of the solvent molecule in the polymer system, and therefore its glass transition also decreases. So this is something which is exploited quite a lot in polymer to, for example, the fact that we use PVC and we can make pipe out of PVC is only because there is a plasticizer that is added. And that's another reason we also would say that, you know, using PVC things on our body or in is not such a great idea, because there are plasticizers, or in interior cars, all of those places, not just the monomer which could be carcinogen, but the plasticizers could also escape with time and they may have other health effects, because plasticizer is being added to increase its processability to manipulate its shape during processing. So maybe it's 4 o'clock now, this may be a good place to stop, and then I think maybe I can resume. I have reached 25 out of 47, which is also halfway exactly, I mean somewhere halfway. So maybe we'll stop here and then resume tomorrow morning.
Can I ask a quick question?
Yeah, sure.
Yeah, so that cross-linked polymer you showed some G prime G double. I was wondering that intermediate range, what is happening, like why that G double prime
So that's where the segmental sort of modes take over, and they are able to dissipate energy. So very high in frequency, even segmental motion is not possible.
I see.
At very low frequency, it just segments can deform because of entropy. They have to come back again. So it's elastic. It's in between where the subsegmental motions leads to dissipation.
They can dissipate.
Yeah. So that's why then G double prime is greater than G prime in that. And whenever we are using rubber for vibration isolation, it should hopefully be in that kind of a range.
Those frequencies.
Yeah. So generally they will use this natural frequency of a rubber, they will say, is basically the peak in G double prime, where it's dissipating maximum energy. And whatever vibration you are trying to, isolate, hopefully should also be in the neighborhood of that frequency.
Okay, thanks.
Okay. So we'll meet tomorrow at 10:30, right? 11, yeah. Yeah.
Okay, if no other question, let's thank Vijit. Outside there will be coffee. Yeah.